Let's try with more example on the eigenvalue and eigenfunction. We are going to find all the eigenvalues and eigenfunction for this ODE. For this ODE, we can assume the solution to be a sinusoidal wave here. After you differentiate twice, you should obtain y double prime equal to this. And you see this term is exactly the same with y here. Therefore, you can substitute inside to obtain the negative omega square y. So you can substitute this term inside here. Collect the term for y here. Then you should be able to obtain this eigenvalue problem. The solution y cannot be 0. Therefore, the determinant for this term must be equal to 0. And from here, you can find your eigenvalue equal to omega squared. From here, your omega will be equal to square root lambda. And the corresponding solution y here is consists of the omega. Once you success to find the A1 and theta 1 from this boundary condition, then you can obtain the y, which is the eigenfunction. Solving this ODE problem is difficult because the lambda is unknown here. Therefore, we need to assume the lambda to be 3 cases. For the first case, you need to assume the lambda equal to 0. So substitute 0, you obtain your y double prime equal to 0. Lambda might be a negative value, so we assume it to be negative alpha square, where the alpha is greater than 0. After you substitute the lambda equal to negative alpha square inside, so this is the ODE that you are going to solve in the second case. For the third case, the lambda might be positive. Therefore, we assume it to be positive alpha square, where the alpha is greater than 0. So substitute the lambda inside, you should obtain this ODE for the third case. Let's solve the ODE for the first case. So you have the y double prime equal to 0. Previously, you learned how to use the integration method to solve this. In fact, you can use the characteristic equation approach to solve this because this is homogeneous ODE. So you can have the r square equal to 0 from here. Then your r is repeated 0. Therefore, your y solution will be in the exponential ry. Then you substitute the repeated root inside here. You obtain two solutions in the exponential 0y. Since these two are dependent to each other, therefore you need to do the treatment. For the second solution here, you need to multiply it with the y, which is the independent variable. So you take the superposition for these two solutions, and don't forget multiply the constant C1, C2 for each solution. Exponential 0y give you 1, therefore you obtain your capital Y equal to C1 plus C2y. So this is the general solution for the ODE. And to find the C1, C2, you need to apply the boundary condition, which give you the particular solution. Let's apply the first boundary condition, which means when your small letter y equal to 0, your capital Y will be equal to 0. So substitute small letter y 0 inside, your capital Y will be equal to 0. Therefore, you obtain C1 equal to 0. Substitute the C1 equal to 0 inside this general solution, so this can be cancelled. Therefore, you obtain the capital Y equal to C2y here. So let's apply the second boundary condition. So here it means when your small letter y equal to 2 pi, your capital Y will be equal to 0. So let's substitute inside, then your capital Y will be equal to 0 when your C2 multiplied with 2 pi. To make this 0, then your C2 must be 0. Therefore, you obtain the coefficient C2 equal to 0 here. Since C1, C2 are equal to 0 for both cases, therefore once you substitute inside, you obtain 0 for the capital Y. So you don't have any solution because capital Y cannot be equal to 0. For the first case, when the lambda is equal to 0 here, you obtain the y equal to 0, which means there is no solution for this case. Then we proceed for the second case here. So solve this by using the characteristic equation approach, where the y double prime is converted to r square, negative alpha square y is converted to negative alpha square, which is equal to 0 here. solve this equation, then you should obtain the root equal to plus minus alpha. Since the root is real number, therefore we can obtain the first solution and second solution in the hyperbolic sine and cos format. You should have learned how to convert this exponential format to the hyperbolic sine and cos format here. Hyperbolic cos and sine format here is more useful to find the particular solution instead of the exponential format. Therefore, we just focus on this. Let's apply the first boundary condition here. Substitute the y equal to 0 inside. So this will be equal to 0. And then substitute the capital Y equal to 0 inside here. Then you obtain here equal to 0. So hyperbolic cos 0 will give you 1. So you need to recall the hyperbolic cos function is like this. The hyperbolic cos at 0 here is equal to 1. Therefore, we can substitute 1 inside. For this term, you need to recall the hyperbolic sign to be like this. Hyperbolic sign at 0 will be equal to 0. Or you can just use the calculator to compute these two terms, and you should obtain these two answers. So this term can be cancelled, then you obtain your C3 equal to 0 here. Since your C3 is equal to 0, so this term can be cancelled. Therefore, you obtain your capital Y equal to C4 multiplied with the hyperbolic sign term. We continue to apply the second boundary condition here. So your small letter y is equal to 2 pi. Substitute this inside here, you obtain 2 pi alpha here. And your capital Y will be equal to 0. So you have 0 here. Let's check this component. You know that the alpha is always greater than 0, means it's always positive. 2 pi is always positive as well. Therefore, 2 pi alpha will be always greater than 0 or positive. Hyperbolic sign a positive value will be in this region, where the hyperbolic sign alpha 2 pi will be always greater than 0, which is positive here, as you can see over here. And it is not equal to 0. If the hyperbolic sign term here is not equal to 0, then your C4 must be equal to 0. So with that, you substitute the C3 and C4 inside this general solution. You obtain your capital Y equal to 0. There is no solution for this case when the lambda is equal to negative alpha squared. For the third case, we are going to solve this ODE. Let's apply the characteristic equation approach to convert the y double prime into the r square, alpha square y to the alpha square. So you solve the root to be plus minus alpha I. Since this is imaginary number, therefore we can have the solution in the cos and sine format. We prefer to use the sine and cos format instead of the exponential format here, because this is more useful to solve the particular solution. Therefore, we do not use this for this case. Let's apply the first boundary condition. So your small letter y equal to 0. Substitute the y equal to 0 inside. You obtain this. Then your capital Y will be equal to 0. You know that cos 0 is 1, sin 0 is 0. Therefore, this term can be cancelled and you obtain the C5 equal to 0. Substitute the C5 inside here. Then you obtain the capital Y equal to the C6 sin term here. To make this term equal to 0, it could be either C6 equal to 0 or sin 2 pi alpha equal to 0. Let's assume C6 equal to 0, so you substitute inside, you obtain 0. So you have the C5 and C6 equal to 0. Substitute inside the general solution, you obtain your capital Y equal to 0. So if this is the case, you have no solution. Let's continue with the second possibility here. Let's look at this term. You have 2 pi alpha, and you know alpha is greater than 0. So 2 pi alpha will be greater than 0 as well. It means that this term is positive, and you are going to compute sine positive value. From the sine graph here, sign positive value is within this region. And you found that the sine 2 pi alpha here is equal to 0 at pi, 2 pi, 3 pi, and so on. So we can say that the sine 2 pi alpha can be equal to 0 when the 2 pi alpha is equal to n pi here. So n is equal to 1, 2, 3, and so on. Since we proved that the sine 2 pi alpha here can be equal to 0 when the 2 pi alpha is equal to n pi, and the n is from 1, 2, 3, and so on. Therefore, our C6 is not equal to 0 in this condition. From here, we can cancel the pi and you obtain the alpha equal to n divided by 2. Therefore, we obtain n number of the y solution, and you have the n number of the C6 coefficient multiplied with the sine alpha y, where the alpha is equal to n over 2 here. So this is the solution to this ODE. And we know that the solution to the differential equation here is called the Eigenfunction, which is the same solution here. Lambda is the eigenvalue in this case, where you have the lambda equal to alpha square, which is equal to n square over 4 after you substitute this. You can also obtain the eigenvalue from here as well, where this is your frequency. Take the square root of it, you obtain the lambda, which is the eigenvalue. Take the square of n divided by 2 here, you obtain the same answer for the eigenvalue. In fact, you have the infinity solution for the capital Y here. First solution, you substitute the n equal to 1, you obtain the first solution for the capital Y to be this, and then you substitute n equal to 2 inside, you obtain the second Y solution to be this. And you can continue up to infinity, so you can find the total solution by taking all the linear superposition of all the individual solutions. So your total solution will be equal to the summation from n equal to 1 to infinity for the yn solution here. This is the final solution to this ODE. Through this example, you should have learned how to obtain the eigenvalue and eigenfunction for this differential equation, and also you learn how to use the eigenvalue and eigenfunction in order to find the total solution.